With that, I will get us started with our first panel. So the first A in NASA is aeronautics, and that's important to not just NASA, not just the industry, but everybody. And so we wanted to talk about a lot of the advancements going on in the A of the aeronautics of NASA this morning. So we're going to This session is once again very generously sponsored by BWX Technologies. Leading our discussion today is Lee Noble, Director of Integrated Aviation Systems Program at NASA. Lee is responsible for the overall planning, management, and evaluation of the Directorate's efforts to conduct experimental flight research and to test the most promising concepts and technologies from across the ARMD portfolio at an integrated system level. With that, Lee, take it away. Thank you.
Thank you very much, Jim. And good morning, everyone. Welcome to day 2. It's a real pleasure to be here and to have a slice of the agenda to talk about aeronautics at NASA. It's a real exciting time. And as you'll see, as you hear from the different panelists this morning, of course, aeronautics is something that touches all of us. If we traveled here on a commercial aircraft, something that NASA has developed, a technology, a capability, is something that you benefited from in getting here. And so that really is the focus of our work. It's not just developing cool technologies and then proving that they work, but it's really what are the best ways to do that so that we can actually make sure that they have benefit for the American public, that they benefit U.S. industry, really that as U.S. taxpayers, the benefit of aeronautics is clear in your everyday life. And so if you go to the first slide, what I wanted to do today is talk just a little bit about the portfolio as it is. There's another slide, I think. And that's represented by the folks that are here on the stage. And what I'll do is roll through that portfolio just with a couple brief comments, and then I'll introduce each of the speakers. If you click once, the first project that we'll talk about is the X-59. It's the low boom flight demonstrator. This is not a prototype for supersonic flight, but this is an aircraft that is designed to demonstrate a quiet, what you might call a sonic thump. If you've ever heard of the sonic boom, you understand how disruptive that is, and it really gets your attention. But what would it be like if it was just kind of a thump that sounded like distant thunder or a bus driving by? So Eric Schrock will talk about that here in a few minutes. He's represents our partner, which is Lockheed Martin, for that effort. Then we'll talk about the electrified powertrain flight demonstration. This is an interesting one because it really is a first ever demonstration of megawatt class electric machines in flight. That's groundbreaking. It opens all kinds of space for what's possible in the future. We have 2 partners for that, actually, as part of that demonstration, General Electric Aerospace. And so Ariane Hegeman will give you an update on what the work that's going on at GE toward that demonstration. And then Nuno Taborda from magniX will also, as our other partner, will talk about their efforts that are similar but different associated with electrified aircraft propulsion. The next activity we'll talk about is the sustainable flight demonstrator, and that, if you've seen the press since AAA Aviation, you saw there's a new X-plane in the mix, the X-66, and that is the sustainable flight demonstrator. Our partner for that is Boeing. And so Lorette Leahy will give us some perspective on Boeing's focus for that, the purpose of the demonstrator, and where they are currently in the process. And then the last thing we wanted to do is yield the mic to Nateri Madhavan to give a NASA perspective on how these different technologies get to flight, the significance of them, and the different sizes and shapes. And if you see at the bottom of that chart, there's something called Flight Demonstrations and Capabilities. And that's the place where we do an ongoing project where we do small flight demonstrations just to do some early TRL research to understand things in a relevant environment. But we also have something on the blueprint, which is a future flight demonstrator. Not sure what that's going to be yet, but as we assess technologies that could be of value in the future, we have something on the calendar for the future to plug those into. So what I'd like to do is start with the low boom flight demonstrator. And so for that, Eric Schrock will give us an update on the work that's being done in concert with Lockheed Martin. Eric is the Director of Technology Roadmaps at the Lockheed Martin Skunk Works. He's responsible for technology development and transition for air vehicle, mission systems, and signature management technologies for all Lockheed Martin Aeronautics programs. He's been with Lockheed Martin for approximately 30 years and earned degrees in aerospace and mechanical engineering from Virginia Tech and an MBA from the University of Tennessee. So Eric, over to you.
Great, thanks Lee. Hopefully everybody can hear me okay. First, let me just start out by saying on behalf of Lockheed and the Skunk Works, we're extremely proud to be partnered with NASA on the construction of the X-59 low boom flight demonstrator as part of the overall Quest Quiet Supersonic Technology mission. And the reason why is that the X-59 has the exciting potential to really open up a new chapter in the world of aviation. For years, ever since we've been capable of supersonic flight, we've not been allowed to fly supersonically over land because of that disruptive sonic boom that is created. In Concorde, even when it was in service, it laid down about 105 dB carpet of awesome noise. For those of us in this room, we recognize that as a really good thing, that sound of freedom. But everybody doesn't feel that way. I don't know why. I'm disappointed in that too, as I'm sure we all are. But with that sound, we were not allowed then to fly faster legislatively over land because of the disruption that that would create. But thanks to visionaries at NASA, we have come up with ways to design aircraft such that we can minimize that sonic boom. X-59 represents that first airplane designed from the ground up to have a low sonic signature and supersonic flight. So we do that through a variety of ways. Really, it has to do with minimizing the strength of those shocks and then preventing them from coalescing so we don't get that rapid, yeah, I did it, the sonic boom that you hear, boom, boom, like that, when you getting that sharp N wave and at the flying faster than Mach 1. So with X-59, we've got the design such that those shock waves are minimized, and we'd be looking at a sonic signature not at the Concorde level, but at around 105 dB, but more like 75 dB. Think of that as a sonic thump, as you mentioned, Lee, sort of about the sound of a car door closing from about 25 feet away, and wondering, you know, how disruptive would that be compared to the giant sonic booms that we're accustomed to currently. So the Quest mission has 3 phases, as you can see there on the left-hand side of the chart. The first one is the construction of the aircraft itself, and that is almost complete. And from there, after initial envelope expansion type flight tests, we'll go into phase 2, which is characterizing the sonic signature of the aircraft both on the ground through an array of microphones and also in the air by flying in close proximity to it with specially instrumented aircraft as it flies faster than Mach 1. And then after that, in phase 3 is where the rubber really meets the road, where we'll overfly communities of people like you and me, and those people that don't like those sonic booms. And they get to hear what that sonic thump is like, and then that data will be collected, you know, the perception data of actual humans on the ground will be collected and then presented to international rulemaking bodies so we can take the legislation that's right now a speed limit that says you can't fly faster than this, and we convert that into a noise limit, where it says, we don't care how fast you fly, as long as you're no louder than this. And that will be used to open up a new way of air travel for all of us, which is really great. That's kind of making this airplane having a legal mission, if you will. And our lawyers at Lockheed get really excited when I talk to them about it that way. And they're like, wow, maybe we could take, instead of a combat aircraft where we stencil how many enemy airplanes we've shot down on the nose, maybe for every regulation we repeal, we could stencil a little scale of justice on the nose of the X-59. So on the other side there, you can see what the airplane looks like. Just recently, we've taken it out of our assembly facility and rolled it to the flight line. And it's a beautiful airplane looking unlike anything that's really ever flown before, and that's exciting. That captures the imagination and really shows the promise for the future, which all of NASA's aviation portfolio holds, and you'll hear about from everybody else today. So thank you. This is why I'm excited about X-59 and proud to be a part of it, because it holds promise for all of us in bringing people together faster. Thanks.
Thank you, Eric, very much. Our next panelist is Arjan Hageman, and Arjan is General Manager of GE Aerospace Advanced Technology Organization. He leads the team of engineers designing, testing, and maturing technologies for the next generation of aircraft. He brings to this role 25 years of aerospace engineering experience, and previously led the development of the CFM LEAP 1B product line through all phases of the new product introduction. He brings his experience of seeing an engine from concept to service to the advanced technology team helping invent the future of flight, and is a key partner for us in the electrified powertrain flight demonstration. Arya?
Thank you. Thank you for inviting us again to be part of this symposium. I'm proud to be here, proud to represent GE Aerospace, and proud to represent a very large engineering team that pretty much on a daily basis is collaborating with NASA on our future of flight. To kind of bracket our opportunity and responsibility there, first let's build the case, climate change. Right? Every day the headlines talk about the high temperatures in the northern hemisphere. Not quite every day, but very recently, massive flooding in the Northeast. Climate change is real, it's happening. And it's extremely important for all industries to get to carbon neutral futures. We are part of that. We're taking a very proactive approach. We're strong believers that it makes a very good business case to have products in the future that meet that challenge. So we're taking a leading role in the industry. And it's not just talk. There's a massive amount of investment that goes with that. We have over 1,000 engineers working globally towards that future of flight the way we envision. And NASA is an incredible partner with us along the way. On the next page, we show the key pillars of that future. It's electrification, where we partner with NASA and Boeing on the EPFD program, where in the middle of this decade, we will be demonstrating a turboprop application where we have a 1 megawatt class electric motor generator combined with a CT7 turbofan, and we're gonna fly it. We're far along on our way there. We started on the electrification route over a decade ago. And every single year, we've pretty much hit a world first milestone. It started with an F-110, where we had a 1 megawatt power extraction on that engine and demonstrated that we were able to operate the engine. Every year, there was a new milestone. Last year was where we demonstrated the whole electrical system, integrated electrical system, at simulated altitude here at NASA Glenn. That was the last step that really got us towards flight readiness. We're now working on finishing the details on that design, procuring the hardware, procuring the engine, integrating it with the engine, and moving forwards towards a ground demonstrator and then a flight demonstrator. But it doesn't stop there. The lessons we're learning in the EPFD program, in this partnership, immediately start transferring over to other demonstrators that we're working on. The biggest one that we're working on is our RISE program, most recognizable by its open fan architecture. It gives a tremendous amount of propulsive efficiency. We're combining that with a compact core that we're collaborating on in the NASA partnership in the high-tech program. And that will be an electrified compact core to get even more systems level efficiency for even lower fuel burns of that integrated system. So the whole concept there is you have an open fan architecture where you have no fan case, no drag, and you can get to an incredible high bypass level. To put that in perspective, we're demonstrating this at a narrow body thrust class application. So roughly a 30,000 pound engine. The diameter of that open fan is the size of our 9X engine, a 777 wide body application. So you have this massive fan that isn't really that much bigger than the current outside diameter of a LEAP nacelle. So installation is very feasible on an aircraft. You're combining that very large fan with a business jet sized core. That's how compact we're talking about. And again, it takes a lot of technologies that we're demonstrating within the high-tech program. Within that program, we have PEX, the power extraction program, that is going to demonstrate we can get even more efficient in that core by the electrification of that engine. That as well is headed towards the middle of the decade timing demonstration. So it's not just EPFD where we're demonstrating it at a turboprop. It's taking those technologies as we're learning it and start feeding that into the other demonstration that we're doing in the RISE program. We're investing in this big time. The most recent announcement we did was at our epicenter down south in Dayton, where we're adding a test cell for about a 20 million investment. The reason? We're just at capacity with the current test cells that we have, and we're doing so much, not just towards EPFD, but also towards RISE and starting to get product focused. We need that extra capacity. On the next page, it kind of summarizes it again. So we have this EPFD demonstrator. It's gonna fly in the middle of this decade. We're close to that. Out of that, we'll immediately start focusing with the technologies that we're demonstrating at that point at the TRL6 level, what we're gonna do from a product application. In parallel to that, again, we're taking the technologies that we're demonstrating, and it's already happening along the way with, say, last year's milestone of the high altitude simulation, and we're start feeding that into our other demonstrators, which are also flying in the middle of the decade. Again, with a very detailed, focused, and intent to get to products that start going into the market in the middle of next decade. Great time to be an engineer, great time to be partnering with an organization like NASA that has really helped us progress much faster than we could have done on our own. And we believe that this will make a key difference in our future to get to that net zero aviation industry. Thank you.
Thank you, Arjen, very much. Our next panelist is Nuno Taborda. Nuno is the Chief Executive Officer of magniX in Everett, Washington. He's an accomplished aerospace executive with 2 decades of experience driving business performance and delivering pioneering technology programs from proof of concept through certification, entry into service, and scaled production. Prior to magniX, Nuno served at Rolls-Royce, most recently as Senior Vice President of Production Programs. He was previously the executive responsible for the entry into service of the Rolls-Royce Pearl 15 engine. This was the first member of a new engine family for the next generation of Rolls-Royce powered business jets. Under Nuno's current leadership at magniX, the company is working to advance its electrical propulsion systems towards certification and production at scale. And again, magniX is our other partner in the electrified powertrain flight demonstration. Nuno?
Good morning, everyone. It's a pleasure being here. I would like to thank our hosts and the American Astronautical Society and NASA for hosting us. It's a pleasure. I'll take you through a bit of the journey of what magniX is all about and what we're doing in the decarbonization of flight. And thank you, Arjen, because you just saved me 2 minutes of my speech, because he made a compelling case why we need to decarbonize flight and decarbonizing aviation and pretty much every single element of our society today. But magniX is a relatively small company. We are 100 people. We started out in this journey over 15 years ago. This goes back all the way to 2007. And the genesis of magniX is really an R&D lab trying to develop some blue sky thinking, R&D technology, electric technology, and then they realized the engine they had developed, the motor they had developed, was really fit for the aviation industry. High torque, high density power, and then we also developed the power electronics and eventually the powertrain to go with it. So magniX started in Australia, moved to the US in 2020. And since then, it's pretty incredible. Over the last 2.5 years, we managed to have 5 world firsts. And that's why I decided to go for pictures rather than wording. A picture tells 1,000 words. And as you can see, the 5 key flight demonstrators that we had since 2019, we started with a small 4-seater, fully electric, the Beaver. We call it the Beaver. Then we moved to a slightly bigger aircraft, the Caravan, fully electrified. And we moved in power range. We went from the 500 kilowatt to the 650 kilowatt. Then we proved the concept in rotary wing. So all the eVTOL hype that you see, well, they already exist and you can fly them. They're called the helicopters. And then you also have the fully clean sheet electric aircraft demonstrated through the Alice Aviation. That was a really exciting moment in the aviation industry. The first clean sheet at that scale aircraft to be flown. And we demonstrated that not only you can do the small aircraft, but eventually you can go to big aircraft. And we flew a hydrogen-powered aircraft with Universal Hydrogen, our partners, where one of the engines on the Dash 7 was fully powered by a fuel cell, fully integrated in the nacelle. So as you can see, we've been demonstrating it, and we've been flying it. It's not just on the lab. We've been really demonstrated that it's feasible. Of course, you cannot do it by yourself. And I think that's where the partnership with NASA to the EPFD, it's key. This is a team game. It's a team game not only with NASA, but with industrial partners. And when you look at closing the regulatory gaps, that's probably one of the key elements that we have in this industry, is how do we kind of work with standards committees, with regulatory bodies, to really understand what are the challenges, how are we going to close those gaps. Barrier risks, how do we as an industry, although we're really keen and we want to be the first to certify a powertrain and a Part 33, and we are on the way to do it. This is really a team game. There's no way that magniX by itself will be able to make that leap and really start the revolution of what electric flight promises. Again, that partnership with NASA, the same as G, is incredible. The amount of access we have to experts, the amount of insight you get, the support you get through how do we go and influence the regulatory bodies to make sure that we are putting the right standards on the table is really what it sets us apart in terms of the rest of the competition. Technology maturation and demonstration of ground flight test. We really need to get to the point where we are also proving, as you can see, we have a great portfolio of world first. We need to start proving that that flight is possible on the Part 25. So we are going to certify on the Part 33, and eventually we want to take it to that scale. How do we enable the future of flight? That's the big question. And it's easy. It's easy in my head. It's been a long journey, and it's going to be quite a hard one to get over the hump. But it's starting from the FAA certification. So everything that we've been doing for the last, I would say, 7 years has started with how are we going to certify this engine? And that's why I said, we are really keen to progress as fast as we can. But unless if the standards are right, we understand what are the things that we need, the means of compliance we need to prove to the FAA, it's really impossible to go and do it. And for the right reasons. We need to make sure that we have strong regulatory bodies kind of governing the safety and the airworthiness of those aircraft. Our entry into service is going to be in the second half of this decade. We truly believe the future is electric. It begins with the regional aspect, the small commuter aircraft. As long as you get to the 300 watt-hour per kilogram type battery pack at the pack level, you start having aircraft that will be able to do operations of short regional and commuter type missions. And then stepping up in size, because eventually, and I think that's where there's a good overlap with the GE work, eventually you want to start getting up in size to really make an impact. That's the only way to really decarbonize. It's not just by changing. That said, the technology will enable eventually to operate in a very different way. Today we have the hub and spoke model. The reason is because we decided to go for big aircraft. It was more economical for the airlines to fly that way. Once you have a lower cost, more efficient aircraft that maybe can fly point to point, that opens up a huge opportunity for companies like magniX and other companies. But eventually you need to get to that big size, longer distances. And the way that you get that, it's stepping up to the hybrid type solution that, so the EPFD is the the prime candidate for that, and eventually going to the hydrogen fuel cell powered aircraft or burning hydrogen in the future. But those are kind of the steps how we see that will enable us to have the future of flight having a brighter future and helping us decarbonize society. Thank you so much.
Yeah, thank you, Nuno, very much. Our last industry partner represents the Sustainable Flight Demonstrator and our partnership with Boeing. That is Laurette Leahy, and she is the Senior Director of Flight and Vehicle Technology for Boeing Research and Technology. In this role, she ensures technical excellence in flight engineering disciplines across the enterprise. Laurette also leads the Flight and Vehicle Technology team for Boeing Research and Technology. She's responsible for technology strategy and research and development in aerosciences, guidance, navigation, control, and autonomy, energy and propulsion systems, and integrated vehicle technologies. Laurette, over to you.
Thank you. So very excited to be here. Let's pull up the next slide. This is when I got this invite and realized that, hey, this is the space community that we're sitting in. Why are we up here? So I'm going to do a little audience interaction with you just to maybe make a point and to wake you up a little bit. But so this is really exciting. We have an actual official X-plane designation, and that just doesn't come with having a prototype flight demonstrator. You actually have to, we own this asset. NASA doesn't own this asset, Boeing does. And so this was an application process. So anyway, very cool and very exciting. I'm going to go into a little bit more detail in the history and how we got here and where we are today, but here's my little trivia question. Okay, so this is a really unique program. It's unprecedented in many regards. So that's a hint, by the way, for my trivia question. So if I had a little model of the commercial crew capsule, the Boeing commercial crew capsule, and our sustainable flight demonstrator, X-66, what do those two things have in common other than being something that the Boeing company and NASA are involved with? Do you guys know what a Space Act agreement is? So this is a really unique Space Act agreement. It's a funded Space Act agreement. So this is a true partnership with NASA, co-investment with Boeing. And again, Boeing, it's consistent theme along here. Couldn't do it on our own. And that's not just a money thing, by the way. It's really tapping into the research, the capabilities, and the workforce, as well as the labs and other facilities that NASA has. So, very exciting to be here. I'll just a little history on this. So, what's the motivation for this particular configuration? We call it a transonic truss-braced wing, TTBW. I guarantee you X-66 is a lot easier to say than TTBW. But it actually started its journey, I would say, almost 15 years ago now. And NASA's vision at that time was really we didn't have the net zero commitment, but it was looking at, hey, we have to be more efficient. And I think the benchmark being used at the time was 2005, kind of state-of-the-art capability when it comes to transport aircraft efficiency. And so there was a phased approach in that time frame to look at different configurations and concepts. What would be the enablers? And you have to take into account not just aerodynamic efficiency, but propulsion efficiency. And so, ultimately, this high wing, high aspect ratio, high wing in terms of where it's mounted on the fuselage was really attractive, and it was the compelling configuration in terms of having a promise of achieving a fuel aerodynamic efficiency itself, with the fuel accommodating future propulsions for the fuel efficiency part. So Ariane talked a little bit about the high bypass ratio. Those in the space business, you probably don't care about bypass ratio, but that is a key measure of propulsion efficiency. If you look at the transport aircraft that you fly on today, the greater efficiency that these modern engines that we have today, those fans are big. And having this high mounted wing configuration allows for those larger fans and the potential of an open fan like Jan was describing as well. So with that, though, comes you have a high aspect ratio. That's that span, and you've got this skinny wing out there. You have aeroelastic challenges, structural challenges. So having a strut or a truss, as we call it, was really required. And there's a nice chart that in those early days when we were looking at, so how does this, what are the different options with this wing? Those early studies, we couldn't even get to transonic airspeed, which if you want to fly like we fly our single aisle aircraft or really any of our transport aircraft, you really need to have a higher airspeed, something around Mach 0.8. And so that goal, along with the aerodynamic and fuel efficiency goals, really drove that configuration that we now call this transonic truss brace wing. So, I said this was almost 15 years ago. You say, gee, why aren't you building them now? This configuration is so novel that our tools, our methods, really have to be validated. So with NASA's help, we've done a great deal of wind tunnel testing, made significant progress in improving the configuration. But to get a configuration, a novel configuration to flight and gain confidence that we can actually make that investment to influence our future platforms. Again, we're targeting that, those mid-2030s as well with this goal. So we have to take this to flight. Validating the tools. There's only so much that we can do with computational fluid dynamics and wind tunnel testing. So a great deal to be learned here. I like the theme around it. It is about the knowledge gain. We're not really informing regulatory entities, although, we'll probably have to have a wing fold. So there may be something there, especially when you start looking at integrating systems into this long, thin wing. So let me just outline some of the challenges, and then I'll wrap it up here. So we've got what we call thin wing systems integration, big challenge there. The high lift systems themselves, actuators. We can learn from what we do on the defense side, by the way, with our fighter aircraft actuation systems. Still, it has to be applied in this commercial platform, meeting certification requirements. So again, challenges there, challenges with the propulsion system integration, the fuels just fuel lines. Again, you've got a very thin wing to be able to integrate all of the systems, hydraulics, electrical, etc. Landing gear, and how do you integrate that? If you notice where that truss or strut comes in and interfaces with the fuselage, we've got significant challenges there with the main landing gear integration. There are many other challenges. I think the biggest that I would say from an aeroelastic standpoint are, again, that model validation, the learning that we'll get from this. In parallel, there are certainly additional investments that we have to make. We're actually really anxious to see the outcomes of both the EPFD and high-tech. Additional investments both with NASA and Boeing, with other industry partners too, in parallel. But those things that we have to take to flight to validate this configuration are really what this is focused on. So very exciting. We're we just got the official kickoff in January, and or contract award in January. Targeting a system requirements review, and you might say, gee, you've done all this research, aren't you well past that? We are modifying an MD-90, and so there's a lot of requirements development just for that. The time that we've spent in this prior decade have really been around what we would call a vision vehicle. What does that final product possibly look like? And so now making sure that we are not only modifying the MD-90 to get it to flight with this wing configuration, but we are also going to achieve the learnings that we're seeking here. Thank you.
Yeah, thank you, Lorette, very much. Our final panelist is Naturi Madhavan. He is director of the Advanced Air Vehicles Program and NASA's Aeronautics Research Mission Directorate. He's responsible for leading the Directorate's efforts in achieving major leaps in the performance of subsonic fixed and vertical lift aircraft to meet challenging and growing long-term civil aviation needs, on pioneering low-boom supersonic flight to achieve new levels of global mobility, and on sustaining hypersonic competency for national needs while advancing fundamental hypersonics research. Madhavan, over to you.
Thank you, Lee. Thank you. Can you guys hear me?
Yeah.
Okay. But thank you to our hosts for inviting us to be on this panel. Thank you for the introduction, Lee, and thank you to my fellow panelists for teeing up these very exciting flight demos that hopefully someday will be the future of aviation. What I thought I'd do with the few minutes I have here is to really focus more on the journey that leads to these flight demos and speak to that in some detail. I know we didn't plan this, but Laurette probably hit some of the points that I was going to make, but nevertheless, I might hit the same points again. So what I want to really talk about when I speak of this journey is really, it's a journey of inspiration, a journey of innovation, and a journey of endurance. It really takes a team of dedicated and talented individuals to come together to have a vision for where they want to go, to evolve toward that vision, to develop a roadmap to get there, to get the support from the organization and the stakeholders, to get them to buy into that, to bring resources, sustained resources over a great period of time to the problem, to have the facilities, the capabilities, whether it's in high performance computing or in wind tunnels or ground testing, to bring this all together. And really the key though is strong, sustained partnerships. And these flight demos don't happen from one organization, as you can see. It takes industry, it takes academia, other government agencies, NASA, all working together to make it happen. And I think the composition of the panel that you see here today is reflective of these partnerships. Laurette already, so I want to hit a few points, and what I've done here is to describe this journey is I've captured the 3 flight demos that we've talked about, 4 actually, but 2 of them are clubbed together, I apologize. And I put them together, and then I've added a 4th piece at the bottom, which is similar but yet different, and I want to make a couple of other points with that. So I've put together a few images to describe this journey, really showing the strengths of modeling and simulation, ground testing, that leads up to maturing these technologies where we can demonstrate them in an integrated fashion in flight. So the first point I want to make, and Laurette kind of hit upon this, is the timelines. We live in a world where technology development takes time. I don't want to diss my true friend here, the iPhone, but we cannot follow those timelines in our world. It takes years, decades. The truss-braced wing that Laurette talked about has been on our minds since 2005. That's almost 20 years. Electrification, we've been working electrification technologies since 2012, so that's another decade right there. And we've been working to tame the boom, if you will, since before Concorde. So these things take time, and that's what I meant. The point I was making with regard to sustainment of resources and endurance, the endurance part of this whole story. The second one I want to stress is the role that modeling and simulation plays in everything that we do. It really touches everything. And we've come a long ways from the days where we used to do 2-dimensional predictions of Euler flows over wings to where today we can capture full aircraft configurations with high fidelity, physics-based models, high lift configurations, landing gear deployed, and really help push the envelope in trying to get to these novel configurations like Laurette was already talking about. So modeling and simulation, we've come a long ways. There's more to go. We have the physics in these models. We are now drawing data-driven models with AI and machine learning. So there's an exciting future out there as well. I think we're getting with this digital transformation and with the digital twin, we have the ability now to not just create a computer twin of a as-built aircraft, but also to recognize how it will perform as it gracefully ages in service. So this is great stuff. So this is another key piece that we've leveraged in all the journeys we've had leading up to flight demos. We've used it for the truss brace wing. The Quest, the X-59, at its core is really a demonstration of modeling and simulation. Our ability to understand and predict the shock wave structure emanating from a supersonic aircraft, how it propagates to the ground, and how to solve the inverse problem. How do you decide the maximum noise that you can handle, the maximum boom you can handle, and how do you take that back and now reshape that outer mode line so that it conforms and produces the boom that you want, or the whisper that you want, I should say. So I think modeling and simulation is a big piece. The second piece I want to stress is ground testing capabilities. We have a lot of facilities at NASA. They need care and they need nourishment, but at the same time, they're very, very effective in helping us not just take our models and simulation to the next step, but also to validate and improve the models. And Lorette spoke to that as well. It's not just the facilities at NASA, it is facilities across the world. We work very closely with partners, the European wind tunnels, the UK, with Japan, and all these are part of the community trying to advance the future of aviation. The final point I want to make is with regard to that last, one more point on the testing capabilities. When it came to electrification, this was a new area to us, and so we had to step up in front and try to develop some of these testing capabilities, just like to develop the modeling and simulation. So what we ended up doing, and many thanks to the folks here at Glenn Research Center who stepped up with support from the mission programs to put together a electric aircraft test facility out here in Plum Brook, Ohio, which has been really tremendous, not just for our own purposes, but for industry to come in and test some of their electric components and powertrains. So the final point I want to make is it goes to that last sort of row, and this is a little different. We haven't talked about it today, but it kind of hits upon some of the points I already made. And one is, and again, this is a credit to our co-host at Glenn for having the sustained vision to maintain expertise in this very, very interesting and important technology area of shape memory alloys. They've had support, but it's really their vision that has maintained this over several decades now, and it's really coming to fruition in many ways now. Now, the other point I want to make here is, given the nature of this audience, is this is what happens, magic that happens when the space side of NASA and the aero side of NASA sort of come together. And really the picture there that you see was of shape memory alloys, the folks working toward building a better tire for the Mars and Moon landers of the future. We were having some durability issues, and we're looking to see if we can fix them. And so they came up with some nickel titanium alloys, which, again, by serendipity or just some smart person thinking about it, said, hey, maybe we could use this to build a better vortex generator. And so vortex generators, if you're not aware, are these little tabs you see on airplanes. You can see it out of the window when you fly. So these tabs are very critical to low-speed performance, but they really are a pain at cruise because they cause drag. Well, what if you use smart VGs, which will deploy and tuck away? They'll deploy at landing, and they will tuck away in cruise. And so here you have smart VGs. We've just tested these with Boeing on the Eco Demo last year. We're planning some more tests, and so we're very excited about this. I talked about a journey. I'll close here. I talked about a journey. These flight demos are not the end of the journey. They are just a waypoint. The real journey ends when all these great technologies that we're working make it into product for the benefit of everyone. So I'll stop there. Back to you, Lee.
Yeah, thank you, Madhavan, very much. All right, well, that concludes remarks from the panelists, and now it's a bit over to you because we'll facilitate a Q&A session, and so we welcome you to use microphones in the room if you have questions for any of the panelists, and we'll go ahead and begin over here.
Yeah, my question deals with what's your vision to get to net zero with aircrafts? As background, we know blended wing body can give us higher bypass ratio, right? So that would be a likely demo in the future. But we also know that sustainable aviation fuels, carbon-based ones, are only going to get to 28% of the goal by 2050. So they're about 3/4 of the way short. So going with your hydrogen comment, can we put a doer of hydrogen on an aircraft and cut emissions by 30%, say, in the next 5 years?
So there is no silver bullet that is going to get us there in 2050. So it will be all of the above, right? From a propulsion system provider perspective, we need to get as fuel efficient as we can possibly get to. Because to your point, sustainable aviation fuels and or hydrogen will be in limited supply for quite a while. So the less you demand, the better off we are. And at the same time, you reduce your emissions. So fuel efficiency is a key. The other piece of it is everything else in the emissions, right? This is much more than just carbon. So advanced combustion system, our lean burning combustion system addresses that. And then the alternative fuels. So sustainable aviation fuels. Today there are 7 pathways. Tomorrow there will be more, right? We need many more to build up that capacity. So making sure that the aircraft and the engines are compatible with those new pathways is critical. And that then extends all the way to very alternative fuels like hydrogen. And how do we get to electrified hydrogen propulsion or hydrogen combustion propulsion, right? So it's all of the above, and all those elements are getting addressed by the various pieces in the industry.
Maybe I can add a few words. Maybe just because we are the small company with big dreams, we believe, like GE, that it's going to be a combination of everything. But we really need to start more than just relying on sustainable aviation fuels or improvement of the technology. We really need to start thinking bigger. We need to start thinking about electrifying more aircraft, using more hydrogen, making sure that the infrastructure on the ground is capable of supporting those kind of, because it's not just having the great engines and the great propulsion systems, you need to make sure that you can fly with them to places where you'll be able either to charge them or to refuel them with hydrogen. So 2050 is going to be a heck of a challenge to get there. Can we get there? I think we can. I think we can. It's going to be really challenging, but we need to start doing it now. We need to start small. We need to start putting those aircraft with fully electrified powertrains, demonstrating the technology, making sure that society is keen to start adopting more of those, pushing the technology boundaries, making sure that the regulatory bodies are taken with us, because it's been challenging. But we're all kind of feeling our way through that new world. We have a different perspective, as I said, maybe because we are the underdog and we have big dreams. But if you have a technology that you've been developing for a very, very long time, sometimes it's difficult to let go. And I get it. I used to work for a big engine OEM. And that's why I think this has to be a team game. And it's making sure that we keep ourselves honest and keeping pushing the boundary of the technology.
Just to chime in here on the hydrogen piece, you have to look at the full life cycle of the production, not just the use. That's my only comment there. But there are other factors too. Fleet renewal, new configurations, new engines is really important part of this. I think you touched on the SAF, the sustainable aviation fuels, is really important. Operational efficiencies on the ground as well as in the air. Flight trajectory. Optimization and management, I think, are key parts of that. And I'm probably missing something there, but all of those are important elements of achieving those goals.
Good stuff. Yeah, great comments. Thank you. Great question. Appreciate that. Are there others? Yeah, go right ahead.
Yeah, certainly all this with climate efficiency, all this new technology is a good thing for climate. What are your thoughts about the enormous inertia, capital inertia in the carbon-based industry that we have in this country? I mean, there's so much infrastructure based on carbon transportation. What are you folks up against as you try to champion this new technology?
I'll make a comment and then I'll open it down the line for you all. But certainly the alternate energy sources are already making their way into what we call sort of real life. A lot of hybrid vehicles on the road, increased electrification, but a lot of the infrastructure has to keep up with that. So it's kind of this balance, this dance of the infrastructure keeping up with the availability of the technology. And so I appreciated what the panelists said here a few moments ago about making sure we're kind of ready for those, that the technologies are teed up, but also that we're realistic about the infrastructure keeping up. So it is this very delicate balance moving forward. But when you see large corporations embracing these alternate paths, I think that really is a good indicator that there is a corporate will to move that direction. And certainly from a government regulation standpoint, we see regulations that also nudge industry that way as well. So I think the will is there, but then there are the practical elements of just the infrastructure really being able to keep up. But the technology readiness is certainly on that path. But let me go ahead and just open it up and ask if there are any other comments from the panel.
Maybe I can say it's a bit chicken and egg. I'll ask a question. How many people were driving an electric car 5 years ago? You see the pioneers. How many people are driving an electric car today? Still quite a few, but not as many as I was hoping. But if you look at the just shot myself in the foot. But if you remember, and maybe Washington State is a different state. If I would have asked that question there, I would have seen a lot more hands in the air. I can guarantee that. You just need to look at the car park. But the reason why 5 years ago was really difficult. People were anxious about range. It was really difficult to get access to charging points. You look now, and I can go anywhere I can go anywhere in the US, and I'll be able to travel on my electric car, and I'll be able to access the infrastructure. So unless if you have the demand and you have kind of you start generating that demand, the infrastructure is going to be really slow to adopt it. You're not going to invest billions of dollars in infrastructure if you don't have the demand for that kind of infrastructure. So, that's why I say we need to keep pushing on both ways.
Yeah. The only point I'll add is, at the end of the day, you've got to look at the entire life cycle. These are not easy problems. Decarbonizing is not easy, especially in aviation. But you have to look at the complete life cycle. You can say, I'm flying a hydrogen airplane, and look, nothing's coming out of the tailpipe but water. But where did that hydrogen come from? Is it green, right? Does it take, the chances are it was produced with a lot of electricity. Is the electricity green? So you have to look at that entire life cycle and to answer those questions. I think from an aviation perspective, and I really don't want to talk broader transportation because that gets into areas that I don't understand, I understand even less than I understand aviation. But I think the point in aviation is, there's a heavy reliance or the hope that we will start at least looking at with sustainable aviation fuel, because it's a drop-in fuel. We can put it into existing airplanes. We can start seeing some benefit. But guess what? We right now produce, I don't know, depending on who you talk to, 100 million gallons across the world a year. By 2030, we'll need 3 billion gallons. By 2050, we need 35 billion. How do we get there? So we've now put in, thanks to the IRA, the Inflation Reduction Act, we've now put in some incentives through the DOE, now trying to make, incentivize with policies, with regulations. So government plays some role, but I think it's a bigger picture. But the frustration I feel is that I don't know if the world realizes how big a problem we are facing. And until we realize that, I don't think we will see real change. And that's a personal opinion, not my employers. It may be my employers, but right now it's a personal opinion.
Well, thank you, everyone, panelists, very much. And thanks to the audience for your attention, for your engagement. It's been a real pleasure to give you a snapshot of flight at NASA Aeronautics. And again, thank you for your time. It's been a great session.
Thank you very much.